Pluto is a far-off and baffling planet which was once an individual member of our nearby planetary family. However, continuous upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning openness. They propose that this crisp world is on a potential extreme impact course with Neptune. But how could this end up working, and what may be the outcomes of such a tremendous event? Are we seeing a fascinating, difficult-to-miss event? Or is there something else to this advancing toward an immense mishap? Join us as we look at the potential results of a Pluto-Neptune influence. Pluto, a former planet that was reclassified as a dwarf planet primarily because of its capricious orbit, remains a subject of interest and study in the vast universe. As shown by late estimates by leading examiners, Pluto's orbit is unsafely close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially risky crash between these two planets, which could represent a colossal risk to Earth. But how is such an event even conceivable? Pluto's orbit around the Sun is unlike any other planet in our nearby planetary system. It requires a stunning 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. Yet the interest doesn't stop there. Pluto's path is marked by its extremely elliptical shape, deviating greatly from the nearly round orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, tilted at 17 degrees relative to the ecliptic plane. The way Pluto follows is much more extreme compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its conjunction with Neptune's. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we might expect from their positions in the solar system. This prompts the regular question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational impacts of other planets. The examination of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its surprising path. Unlike other planets, whose orbits lie fairly near the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery grew with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space deals with determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complicated way. The terms Amal libration and degree libration, along with the VZK wobble, are key pieces of this puzzle. According to astrophysicists, what keeps all planets in their orbits is Amal libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned approximately 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Degree libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional layer of protection from potential impacts. Another key factor is the VZK wobble, named after three scientists, Bond, Zippel, and F, who studied how objects move in space. It refers to how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK wobble helps us understand why its orbit around the Sun is so unconventional. Despite Pluto's orbit seeming chaotic, this wobble helps keep it moving smoothly for extended periods. The VZK wobble shows that even when things in space appear wild and erratic, certain patterns and rules maintain some control. All these factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or veer off course. This three-body problem helps us understand how these interactions change based on how these space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, distant worlds, and their stars. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is overall turbulent, with slight deviations in initial conditions leading to massive differences over centuries. However, these unique properties of Pluto's orbit have been found to maintain stability over extraordinarily long timescales, effectively countering the chaos. Later, computer models have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, in which, for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path predictable. However, Neptune isn't the only planet helping with this. Jupiter's gravity also plays a critical role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is sufficient to ensure Pluto stays on a steady path for many years, even billions of years. So it appears that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without encountering trouble. These quirks are significant in the broader context of the universe, maintaining the control and consistency of celestial bodies' movements. Without these stabilizing forces, our solar system would be a much more chaotic and turbulent place. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to impacts on other celestial bodies. For Pluto, especially with the discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. It gives us a clearer picture of the dynamic nature of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can reach a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and study of these anomalies to better understand our place in the universe. Exploring the depths of space often forces us to confront the capricious nature of celestial bodies, and Pluto's orbit is an ideal example of this whimsy. The concept of orbital chaos, referring to the fragile dependence of a celestial body's path on its initial conditions, is vividly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using computational models has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use advanced mathematics to demonstrate how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even tiny changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something truly intriguing about Pluto's orbit. Despite having factors like Amal and degree libration to keep it stable, its path can still be chaotic and erratic. If you start with even a small difference in where Pluto is or how fast it's moving, over many years its orbit can look quite different. However, even with this turbulence, Pluto's orbit remains stable for long stretches, like billions of years. This means Pluto's journey around the Sun has some kind of order to it, even though it might seem chaotic at first. Predicting future events, especially when they involve unstable orbits like Pluto's, presents significant challenges. The inherent predictability of these systems means that long-term forecasts are often fraught with uncertainties. While mathematical models provide a powerful means to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. The turbulent nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder of how our knowledge of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the position of each planet can significantly influence the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and key figure in popularizing cosmology, offers an intriguing perspective on the mysteries of our solar system, particularly the stunning case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the dark realms of space. Tyson's stance on Pluto's renaming is grounded in the ever-growing knowledge of our solar system. He sees the renaming not as a demotion, but as a significant shift in our understanding of the various bodies orbiting our sun. His approach to celestial mechanics is one of continual learning and adaptation. He views the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that as we learn more about space, more questions emerge, challenging us to explore further and refine our understanding. Michio Kaku, another renowned physicist and futurist, complements Tyson's thoughts with his own perspective. Kaku focuses on the often eccentric forces that shape our universe and brings a visionary approach to explaining how we interact with it. He is known for his ability to connect abstract scientific ideas with futuristic concepts. In Kaku's view, Pluto's eccentric orbit is just one example of how unstable forces can shape our understanding of the cosmos. Kaku's work stresses the importance of observation, modeling, and theorizing to prepare us for future space events. He echoes Tyson's sentiments, suggesting that we must remain vigilant and continue to improve our models to better predict potential celestial events. The potential for a Pluto-Neptune collision is not simply a hypothetical scenario. It serves as a reminder of how much there is to learn about celestial dynamics and the unpredictable nature of our universe. Both Tyson and Kaku agree on the necessity for constant observation and research. Their work pushes us toward discovering new and transformative ways of predicting and understanding cosmic events. Through continuous investigation and advanced technology, astronomers will remain ready for whatever the future of space exploration may bring. The general consensus among scientists suggests that for many years to come, the orbits of Pluto and Neptune will remain stable, thanks to their complex gravitational relationship. As a result, a direct collision between Pluto and Neptune is highly unlikely. However, the unpredictable and complex nature of their orbits calls for continuous monitoring to ensure that we understand their long-term behavior and any potential risks. While the likelihood of a Pluto-Neptune collision seems improbable with current models, this case highlights the importance of ongoing research. It stresses the need to continually refine our understanding of the universe. Advancements in technology, including sophisticated telescopes and simulations, will allow astronomers to refine their predictions and improve our understanding of the dynamic forces at play. Tyson's work, which is centered on expanding our understanding of the universe, and Kaku's emphasis on the unpredictable nature of celestial mechanics, both reinforce the importance of continual study and inquiry. The potential collision between Pluto and Neptune ultimately serves as a reminder of how much we still have to learn. With each new discovery and refined model, we strive to better understand the ever-changing landscape of our solar system. One of the most intriguing aspects of Pluto's relationship with Neptune is the concept of mean motion resonance. This phenomenon occurs when two orbiting bodies interact with each other in such a way that their orbital periods align in a simple ratio. In Pluto and Neptune's case, for every 2 orbits Pluto completes around the Sun, Neptune completes exactly 3. This resonance helps keep Pluto's orbit stable by ensuring that the two bodies do not come too close to one another, even though their orbits cross. In essence, this gravitational synchronization acts like a celestial safeguard, preventing a direct collision. Despite this resonance, some astronomers still wonder if Pluto's orbit will eventually become more erratic in the distant future. Could it be that, over millions of years, the gravitational influences of the gas giants, especially Jupiter, might change in such a way that Pluto's orbit could become less predictable? While current models suggest that Pluto's orbit will remain relatively stable for the foreseeable future, minor shifts in the gravitational balance between the planets could potentially cause disruptions. This highlights the ever-present unpredictability of space, where even seemingly stable orbits are susceptible to long-term changes. Furthermore, the study of Pluto's orbit provides valuable insights into the broader workings of the solar system. Pluto's eccentric and inclined orbit challenges traditional notions of planetary formation and dynamics. Most planets in the solar system have nearly circular orbits that lie within a narrow plane, but Pluto's orbit is tilted at an angle and follows a highly elliptical path. This makes it an outlier in terms of planetary motion, prompting scientists to reconsider the formation processes that might have created such a unique body. It also raises questions about the early history of the solar system. Was Pluto once a part of a larger planetesimal disk that was scattered or ejected, or did it form in place, far from the Sun, with a different set of gravitational forces acting on it? Interestingly, the dynamics between Pluto and Neptune could also offer clues about other exoplanets and distant objects in our galaxy. Astronomers are increasingly turning their attention to exoplanetary systems that exhibit similar eccentricities and tilts in their orbits. By studying Pluto's orbit and its gravitational interactions with Neptune, scientists can better understand how planetary systems, including those far beyond our own, might evolve over time. The more we learn about Pluto, the more we can apply this knowledge to our understanding of other star systems. In the long run, the future of Pluto's orbit remains a captivating mystery, but one thing is certain. Its interaction with Neptune will continue to inspire astronomers to refine their models of orbital dynamics and celestial mechanics. As our tools and methods for observing the cosmos improve, we can only expect to uncover more surprising details about the hidden forces shaping our universe.